Now that we've looked at intermolecular forces and are able to identify them in very basic molecules, we need to be able to apply this to much larger molecules. And on the AP exam, that's generally what they end up giving you to evaluate so that they know that you know about your intermolecular forces. So let's look at some larger molecules. These are going to be very basic organic molecules. Here we have an aldehyde. So this is acetaldehyde. And we have, I want you to take a moment and think about what type of intermolecular force you would have. In this one, you are not going to have hydrogen bonding because this hydrogen is not directly attached to your carbon. This is going to be polar because this oxygen is quite electronegative and is going to be pulling on the electrons from all of these other atoms, leaving this entire molecule polar. So it would have dipole-dipole forces. If we look at this one, we recognize that we are going to have some polarity here because we've got our nitrogen and oxygen. Those tend to be very electronegative elements. And we see that we have a hydrogen directly bonded to a nitrogen. So here we are going to have hydrogen bonding. This hydrogen is going to be electron deficient and can seek out either these unshared pairs or these unshared pairs on a neighboring molecule. If you look at this one, this is a nice ether. And we are going to have some no hydrogen bonding because we don't have any electron deficient hydrogens here, but we do have this oxygen sitting here, so it is going to make this entire molecule polar. So it would undergo dipole-dipole forces. Here we have an ester. These are the things that give artificial smells or flavoring, or smells anyway, and we'll make some of those after the AP exam. So if you look at these, we've got this double bonded oxygen here and another oxygen here, but no directly bonded hydrogen, so no hydrogen bonding. But again, these tend to be very electronegative elements, so they are going to pull on those electrons, making this molecule polar. So we would have a polar molecule, meaning dipole-dipole forces. Here we have methanoic acid. This is also called formic acid. This is what fire ants kind of inject into your skin when they bite and makes it itch and burn. This is that COOH that we see on the end of acids, organic acids like acetic acid. And if we look at the type of bonding that we have here, we notice that we've got some oxygens, so definitely some polarity going on, but we do have a hydrogen directly bonded to this oxygen, and that is going to make this be able to undergo hydrogen bonding with other molecules. So we do have hydrogen bonding going on here, and so when you see that COOH, you are going to have hydrogen bonding. That can happen. This is methylamine, and when we look at these, I want you to notice this part right here, and I don't want you to get freaked out about looking at these molecules. An amine kind of acts like an ammonia, and when it's attached to these carbons, it's just like if it were attached to a hydrogen, and it's going to do what this molecule is going to do exactly what ammonia does, and try and collect a hydrogen in order to become ammonium, or collect another hydrogen here to collect that positive charge. And so you would treat it the same way as you would treat ammonia. Just a heads up. So if we just look at this for the type of intermolecular forces, so we have a nitrogen here, so we know we've got some polarity going on, and we have a hydrogen directly, actually two hydrogens directly bonded to this nitrogen. So we are going to have some hydrogen bonding going on in this molecule. Here we have ethane. So this is a very basic alkane, just carbons and hydrogens. Remember, this carbon-hydrogen bond is only slightly polar, and this molecule right here is very symmetrical. So if you get a compound that just has a bunch of C's and H's in it, those are alkanes, and they are non-polar, and it's worthwhile to go ahead and memorize that. So if that is a non-polar molecule, then we are only going to have London dispersion forces. But the more carbons and hydrogens you add, the more those will increase. Here I have an alcohol. We have an oxygen directly bonded to a hydrogen. This is methanol. This is going to be able to undergo hydrogen bonding because we have an electron deficient enough hydrogen that will seek out unshared pairs on neighboring methanol molecules. So any alcohols are going to end up being able to undergo hydrogen bonding. Okay, another thing that they're going to do on the AP exam is give you kind of answer choices and ask which one represents hydrogen bonding. So we just looked at an alcohol, and we know that it will undergo hydrogen bonding. The way this is drawn, these little equal signs right here represent a force of attraction. So is the diagram that I have right here representative of the hydrogen bonding that this molecule will undergo with other molecules of the same type? The answer is no. Yes, we have a hydrogen attracted to an unshared pair, but this hydrogen isn't electron deficient enough because it is not bonded directly to FO or N. So this attraction would not be hydrogen bonding. A better representation of the hydrogen bonding attraction would be this. So this hydrogen that's directly bonded to FO or N, in this case oxygen, is electron deficient and will be seeking out those unshared pairs. So this is hydrogen bonding. On your homework tonight, I have more practice on identifying what hydrogen bonding really looks like, because they do test that in many different ways, and you will have to be able to articulate it as well. All right, now I have some practice, and this will help with your homework. And the reason why we want to be able to identify our intermolecular forces is because they let us know about certain properties that these solutions will have, or substances will have. So the stronger the intermolecular forces between molecules, the higher the substance's melting and boiling points. That means the intermolecular forces are what has to be broken in order for a substance to go through a phase change. You have to break some of those attractive forces for a solid to go to a liquid, and then you have to break the rest of those attractive forces when that liquid becomes a vapor. That's what boiling points are, a measure of how strong the intermolecular forces are. So recognize that intermolecular forces are broken when we go through a phase change, not bonds. Bonds are much, much stronger than our intermolecular forces. And in this homework, I also included some substances that actually have bonds that would have to be broken. So you've got to be able to identify what type of attraction we're dealing with. So remember that atom-to-atom bonds are much stronger than intermolecular forces. These are only about 5% as strong as atom-to-atom bonds are. So in this first one, we're going to rank the melting points for each of these. So the first thing we want to do is we want to go through and identify what type of substance we have here. All right, now let's work a problem with this. So rank the melting points for each of the following, one being the highest. So we need to identify what's going on here. We have several different compounds. We have an amine here. We know just from looking at those structures that this hydrogen is directly bonded to this nitrogen, and so there is going to be some hydrogen bonding. If we look at lithium chloride, this is ionic. This is not a molecule at all. It doesn't have intermolecular forces. It has that strong electrostatic attraction between the positive lithium ion and the negative chloride ion existing in that crystal lattice structure. So we have ionic going on here. The next one is going to end up being dipole-dipole. The compound would look like this if you were to draw it out. And so we have nitrogen bonded to carbons in 3 different directions here. So this is going to be a polar type molecule. There's an unshared pair on the molecule as well. So you are going to have a non-symmetrical molecule, which will result in a polar molecule, which will have dipole-dipole interactions with other molecules of the same type. This next one, we have another amine, and so we're going to have hydrogen bonding again. Now, we have this information. We can make our decisions on which one has the highest melting point. So ionic is much stronger than any intermolecular force, so it takes more energy to break those ions apart, so it is going to have the highest melting point. So we would put, that would be number 1. Then we have 2. Our next strongest is going to be hydrogen bonding. So we have 2 things here for hydrogen bonding, and we have to decide which one basically has stronger hydrogen bonding. And with this one, we're going to go with the larger molecule. Since there are more electrons, there's more polarizing, it's more polarizable, and so our hydrogen bonds would be stronger for that one. So that is number 2, and then our other amine, which has hydrogen bonding, would be number 3. Leaving the dipole-dipole interaction to have the lowest melting point at number 4. Okay, now we have some more practice. Take a moment and see if you can figure out, go ahead and pause the screencast to see if you can figure out the ranking for these boiling points. Okay. What we have here, we have an ester, so this is going to be polar. No hydrogens are directly attached to this, so dipole-dipole for this one. Again, we have dipole-dipole interactions because we don't have a hydrogen directly bonded to F over N. Here we have all C's and H's, so this is going to be non-polar. So we'd have London dispersion forces, and then we're going to have another amine, which we already determined in the last problem has hydrogen bonding. So we want them in terms of increased boiling point. So we want the one with our increasing boiling point. So we want the lowest boiling point first. That means the one with the weakest intermolecular forces. So our alkane here, this would be butane, would be first. Then we have our 2 esters here, which both have dipole-dipole interactions. The dipole-dipole interactions will be weakest here because this is a smaller molecule, so it's less polarizable. And so that would have our next highest boiling point, followed by this one. It's larger, so it's going to have more our higher boiling point. It takes more energy to break those stronger forces of attraction. And then our last one would be hydrogen bonding. So the correct answer would be B right here. Okay, now take a minute and see what you can do with this second problem. All right. In this problem, they're asking you about the states of matter that each of these molecules would be in. Intermolecular forces are the reasons why gases are gases. They have weak intermolecular forces, so it takes less energy to break them. So the temperature, the heat in the room is enough to break those intermolecular forces. If we have stronger and stronger intermolecular forces, if it can break some of them, it's a liquid. If the heat in the room can't break any of the intermolecular forces, then it is a solid. So for this one, we have a nonpolar molecule. We have a nice polar molecule with hydrogen bonding. So this is an alcohol. And then we have an ionic compound. The ionic compound has stronger forces of attraction, so it is going to be our solid. This The energy in the room would probably be enough to break some of the attractive forces, but maybe not all of them. So I would expect this to be our liquid. And F2, it's a small molecule. It only has limited dispersion forces, which aren't going to be very strong because this molecule is so small. So the temperature in the room, or the heat in the room, is enough to break those intermolecular forces. And we would expect this one to be our gas. So the correct answer for this one is A. The stronger the intermolecular forces between molecules, the lower the substance's vapor pressure. The intermolecular forces are what has to be broken in order for a substance to be able to evaporate. Volatile substances like fingernail polish remover or acetone evaporate very, very easily. So do you think they have strong intermolecular forces or low intermolecular forces? Well, the correct answer is low intermolecular forces. That way, the heat of the room is enough to break those intermolecular forces, and then you can smell acetone immediately because it is evaporating into the air. So if we're looking for something that has the highest vapor pressure, we're looking for something that has the lowest intermolecular forces because it's going to be giving off a lot of vapor. If we look at our compounds here, so again, we're looking for lowest intermolecular forces. I see we've got some hydrogen bonding down here on D and E. So we would immediately eliminate those because the others only have C's and H's, so they are nonpolar and would only have London dispersion forces. So now I have to make a decision between those and also the temperatures changing. Well, the difference between A, B, and then C is this molecule is slightly smaller. So it would have lower London dispersion forces if we were looking at them at the same temperature. It's also at a higher temperature than this larger molecule here. So I would say that the one most likely to evaporate more would be C, and it would have the highest vapor pressure because it would have the lowest intermolecular forces. Here's another practice type problem, and in this one they're actually giving you a measurement of the polar nature of the bond, and it does have these units here with a capital D, and it's the dipole moment. So this molecule, which is going to be difluoroethane, has a dipole moment of this, and here's its boiling point. Another very similar, this is dichloroethane, has a smaller dipole moment. So the polar nature of the bonds is a bit less, but it has a much higher boiling point. And they're asking, why is that so? So read through the answer choices and see if you can come up with the correct answer. Okay. I would have to say that D is the correct answer for this problem. This is not going to be, this is more polar, but if they are more polar, they have stronger intermolecular forces. And if they have stronger intermolecular forces, they are going to have a higher boiling point. So this last part didn't match up with the answer. This is not ionic, so that eliminates B. They're both molecules. C does not have hydrogen bonding. Hydrogen is not directly bonded to F over N, so it cannot be C. CH2Cl2 is a much larger molecule than difluoroethane, and because of that, it has a larger molecule. It is going to be more polarizable, and as a molecule, you will have stronger intermolecular forces than in CHF2. The last thing I want to talk about is viscosity. Viscosity is the resistance